All right, in this video, we're going to show you how to find a particular integral surface of a quasi-linear PDE. This type of problem is also called the Cauchy problem of the quasi-linear PDE. All right, in an earlier video, we have shown you how to find the general solution of this quasi-linear PDE labeled 1. We've shown that this is given by f of phi and psi equal to 0, where f is an arbitrary function, and the phi and the psi is a two-parameter family of integral curves obtained by integrating these ODEs here called characteristic equations. Okay, so that has been done in a previous video, so if you want to check that one if you're not up to speed. So this we have shown how you can find using that method, which is called the characteristic method of characteristics. Now this video I want to focus on how to find a particular function f which is satisfied for a particular given curve. So the focus of this video is on the following. So a particular integral surface containing or satisfying a given curve, C can be found. This integral surface is going to be an integral surface of equation 1, of course. Can be found by expressing the general solution we found here, which we have labeled 2. So by expressing 2 in the form, so we make either phi or psi the subject of the formula. So in this case we're going to write it phi is equal to g of psi. Let's call this equation number 4, and then from this from which the functional form of g form of g can be obtained by expressing the given curve C in parametric form, So we express it in parametric form, and then we substitute it into equation number 4, and substituting into equation number 4. Okay, so this is basically what this video is about. We want to find a particular integral surface of the PDE labeled number 1. The curve C is also called the Cauchy data. So remember, we say this type of problem It's called the Cauchy problem. All right, so that is the theory. Let's look at a few examples. All right, so in these examples, we're going to be looking for the particular integral surface of the given PDE satisfying the specified curve C. In example A, we have got x ux plus 2x squared uy equal to u. So we're using the subscript notation here. Ux denotes partial u, partial x. This solution we'll need to find must satisfy the curve u equals 4x squared plus x when y is equal to x squared plus x. Okay, so the first thing we need to do is to find the general solution. For the general solution, we need to integrate the characteristic equations, which will be dx over x equal to dy over 2x squared equal to du over u. Okay, if we first take the first two terms, then this we can write as 2x dx is equal to dy. Integrating this, we're going to find phi is y minus x squared equal to c1. So that is the first integral. And then taking the first and the last terms, okay, so for that one we're going to have dx over x is du over u. This one is telling us that ln u is equal to ln x plus ln c2. So from here, psi is going to be u over x, which is going to be equal to c2. So that means the general solution we can write from here is going to be f of u over x and y minus x squared equal to 0. Now we want to find the particular f so that this solution satisfies this given curve here. Now we said the way to do this is to express this as a function of phi. So what we're going to do is this we can write as this equal to a function of that. So we can write this as u over x equal to g of y minus x squared. In fact, this can write as g of y minus x squared times x. Then we want to write c in parametric form and substitute. However, in this case, you can see that c, we can use x as a parameter, so and then we can write everything in terms of x, because u can write entirely in terms of x, and y we can write in terms of x. So if we do that, u is 4x squared plus x, then g, this is going to be g of y is x squared plus x. So we're simply going to write x squared plus x here, and then minus x squared, so which is that minus x squared there. So we have got 4x squared plus x is equals to x times g of x. And then straight away here we have got the functional form of g. So g of x is 4x plus 1. Okay, and then we can now write the the solution. So if we go back here, if g of x is 4x plus 1, then g of y minus x squared. So we replace every x by y minus x squared. So it's going to be 4 into y minus x squared plus 1. And then we're going to take this and plug it in here. So therefore we're going to have u equals x into 4 times y minus x squared plus 1, and this is going to be our particular integral surface for this problem. Okay, so we're going to look at another example. So let's call this one example number B. Suppose this time we have y squared minus u squared ux, take away, so minus xy uy is equal to xu, and the curve of interest is u equal to y equal to x for x greater than 0. This is just a straight line, of course. All right, so we're going to start with the characteristic equation. In this case, it's going to be dx over y squared minus x squared equal to dy over a negative x over y equal to du over xu. If we take the last two, you can see that x is a common factor there. So we're going to have dy over y plus du over u, this is u, and equal to 0. So if we integrate this, we're going to find that phi is yu, which is going to be equal to C1. Then we can combine, if we combine the first or the last two terms, actually dy plus du, then we can factor out x in the denominator. That's going to be u minus y. Equate this to the first term in the characteristic ODEs. Then from here we can factorize the denominator. I can cancel out the common factor of u minus y. So this thing is going to be dy, so dy plus du over x. Maybe let me just write it below. So we're going to have dy plus du over x plus dx divided by y plus u equal to 0 if you bring everything to the same side. And then this we can write as y plus u dy plus u plus x dx equal to 0. Then integrating this, we are going to find that phi is x squared plus y plus u all squared equal to C2, where we have cleared out the common fraction of 1/2. All right, and so if we write this as phi equal to g of psi, so actually this time we're going to do it the other way around. Write this as psi equal to g of phi. It doesn't really matter which combination you do here. So psi, which we've just obtained, is x squared y plus u all squared, and then g, remember that phi is equal to yu, so this is g of yu. Then our particular curve through which we want the surface to go through is u equal to y equal to x. So again, we can write everything here in terms of x. We can use our x as a parameter. So this is just going to be g of x squared. Here we're going to have x squared plus 2x all squared. So that's going to be 4x squared. So this thing is telling us that g of x squared is going to be 5x squared. So we've got the functional form of g. So then we can rewrite that. So g of yu is simply going to be 5yu. And so the solution is going to be x squared y plus u all squared is equals to 5yu. If we like, we can remove brackets here. It's going to be x squared plus y squared plus u squared is equal to 3yu. It's going to be 2yu this side. If we take it to the other side, then this one is going to be 3yu. All right, we're going to give you one example now to try. So you can just pause the video, have a go at this example, and then once you are done, you can scroll down to compare your answer with the answer we are going to present. So we've got here x y minus u x plus y into x plus u uy, and then on the right hand side we have got x plus y times u. Then the curve that this integral surface must contain is a parabola defined by u equal to 1 plus x squared. Y is equal to x. So this is a parabola. Okay, so have a go at this one, and then you can compare with our answer. So if you just want to press the pause button, have a go, then when you press play, then you can compare with our solution. Okay, at this point we are hoping you've had a go at this C. I'm going to scroll down to show you our solution for comparison. So for this problem, the characteristic ODEs are going to be as shown here. Now if we rearrange the first term and add like this, then you can see that the denominator is going to have a common factor of x plus y with the last term. If we cancel that out, then the ODE will look like this, which we integrate to get our phi. And then for the second combination, if we subtract the first two terms, dx minus dy, Then again, in the xy terms are going to cancel out. Then in the denominator again, we're going to have negative ux plus y, which is similar to what we have for the last term. Cancelling that out, this becomes our dE, which we integrate easily, and this is now our psi. Now so if we let xy over u be equal to some function of the second function psi, and then remember that our curve is u equal to 1 plus x squared, while x is equal to y. So x is equal to y here. So again, we're going to want to write everything in terms of x. So if we write the numerator in terms of x, that's going to be x squared. The denominator is going to be 1 plus x squared. And then the g, the argument of g, x minus y, is going to work out to 0, so it's just going to be u. Now so this is the same combination as that, but we need that one as well. So what we're going to do is we're going to let xi be equal to the argument of g, from which we can see that x squared is just going to be xi minus 1. So we can write this as g of xi is equal to xi minus 1 all over xi, and then that means we are now in a position to write this. So that means our particular integral is going to be xy over u. Now our xi here is x minus y plus u. So in the numerator, we're going to have x minus y plus u minus 1, and then divided by x minus y plus u. So this here is going to be our particular integral surface. Okay, thank you very much for watching.